So this is going to be the second part of 4.1. Again, don't pay any attention to the notes in that it says 4.2. What we're going to be doing here is we're talking about sectors of circles and arc lengths of circles. So I know that you did this in geometry, so we are going to be able to recognize the sector of a circle and find the measures of the arc length and sector area. Some of this you have done in geometry, and some of this you may not have done in geometry. But let's just get to this really quickly here. Let's just review really briefly what we have here. So we're going to call this the center of the circle, which means that both of these are going to be our R, that's radius, the radius of the circle. If you look at this on the outside here, this is what we call the arc. And then on the inside, all this shade that I'm doing, we're going to call that the sector. So we need to know what all three of those are, and that's going to just take us to our next page. So those are the three main components. One last thing that I guess we should probably remind you is that center part where we're going to take the angle. We will call that the central angle. And I apologize about my writing. But let's just kind of move on into what we're going to do with these. So we have two different types, and again, on your paper it's probably a little bit easier to read than here. Theta is in. So if theta is in degrees, we have an arc length that looks like this. Now notice, arc length is going to be represented by S. S equals on both of them. For sector area, for the area of it, that's going to be represented by K. The reason why we use K and not A is because A is usually used for the area of big, like the full circle and things like that. If you used A, it wouldn't be the end of the world, but we use K in this instance. Now, if you notice that if theta is in degrees, we are basically saying piece of the circle. There's 360 degrees in a circle. So whatever the central angle is theta, okay, that's the fraction of the circle we're dealing with. We will multiply that by the full circumference, 2 pi r, to get what the arc length is. So for example, if we had half a circle, that would be 180 over 360, which is 1/2. So we'd have 1/2 times 2 pi r, which gives us the arc length of half the circle, or basically half the circumference. And the same thing is true with the sector area. We have area, or K equals theta over 360 times pi r squared. In other words, fraction of the circle times the area of the circle will give us the area of the sector. Now, if it's in radians, we have actually quite simpler formulas. We have S equals r theta. That's for the arc length. So radius times the central angle. And then we have K equals 1/2 times r squared times theta. Again, that's radius is the r, and theta is the central angle. Now, we do have this extra equation down here. It says K equals 1/2 r times S. So real quickly, I want to show you where this formula comes from. And it really comes from the sector area formula, because if you notice up here, what I can do is I can rewrite this formula, K equals 1/2 times r times theta. So basically, if I break up the r squared into r times r, you should notice that we have an r times theta, which is exactly the same thing as S. So that's where the 1/2 rs comes from. So if you know S and you don't know theta, then you're able to still find the sector area using your radius and your S. Okay, so we are going to use these formulas to do a couple of problems. So let's just get to it. Okay, we want to find the arc length and sector area of the following circles. So in this circle, we are given a radius of 12. So our radius here is 12. Okay, and that's 12 inches. And our theta that is given to us is 100 degrees. So if we start using our formula, first of all, we have to identify that we're using degrees. So we're going to use the degree formula. S equals theta over 360 times 2 times pi times r. And then we can plug these values in. So we have 100 over 360 times 2 times pi times 12. And then we can start to simplify. And many of you guys may simplify a different way. Some people just multiply across the top of the fraction. I like to try and simplify, as much as I can before multiplying. So I can, if I divide the top by 5 and I divide the bottom by 5, I get 20. And then the bottom becomes 18. 360 divided by 5 is 72. And then we can keep going. We can get rid of our 2, make it a 1, make this a 36. We can keep reducing all the way through. So I'm going to kind of get rid of this right now, but the idea is that I don't want you to think that you have to reduce any specific way. The idea is once we plug all of this in, we should end up with 20 pi over 3 inches. And again, you guys can plug that in on your own and simplify the way that you want to. Some of you will multiply straight across the top and then divide by the bottom. Some of you will reduce as you go through it. Okay, so that is our arc length. So let's talk about the area. K equals, again, because we're in degrees, theta over 360 times pi r squared over 1. Plug these values in, and we get 100 over 360 times pi times 12 squared over 1. We start eliminating things. We get divide by 20, divide by 20. So we get 5 over 18. This becomes 144. So maybe divide by 2 and divide by 2. So we get 9 and 72. And then we have 72 divided by 9. That becomes 1. And that becomes 8. So 5 times 8 is 40 pi. So our area here is K equals 40 pi squared. And again, if it doesn't make sense or doesn't follow how I simplified that, then you go through and multiply it through on your own and figure out how to get 40 pi inches squared on your own. You don't have to follow, what I just did is still elementary or middle school math, but if you don't understand the way that I did it a little bit quicker, then you just take a few more steps and do it on your own. But either way, you're using a formula and simplifying after you plug values in. Okay, let's do one where it's in radians. Okay, so now we have radians. We have 2 pi over 3 as our radian. So now we have different formulas. So we're going to use S equals R times theta. Much simpler formula. S equals, and in this case, 6 is our radius, so 6 times 2 pi over 3 equals 6 divided by 3 is 2. 2 times 2 is 4 pi inches. So that's our arc length. Now we can do our area. K equals 1/2 r squared theta, which equals 1/2 times 6 squared times 2 pi over 3. 6 squared is 36. Half of 36 is 18. So we end up with 18 times 2 pi over 3. 18 divided by 3 is 6. 6 times 2 is 12. So we have 12 pi inches squared. And again, using a formula, plugging values in, and simplifying. And notice we keep everything in terms of pi when we can. So the next example, this is kind of going to intertwine that extra equation that we dealt with. So they give us some information. A sector of a circle has an arc length of 6 centimeters and an area of 75 centimeters squared. Find its radius and central angle. So basically what we're looking at here is we have we're given our S, that's 6 centimeters. We're given our K, that's 75 centimeters squared. What we're not given is we are not given our radius and we are not given our theta. So we have a little bit of a problem because usually we use both of these, or we use one of them, or sorry, both of them for both our arc length and our area, but we don't have either one of them. So what we want to do then is maybe look at that extra formula that we were taught. So we have two formulas right now that we've used so far. S equals R times theta and K equals 1/2 R squared theta. And like I said, because we don't have either R or theta, we can't really use these formulas. But what about that extra formula that we have, 1/2 times R times S? Well, we have our K and we have our S. So that means we can put 75 in for K. And we can put 6 in for S. So we end up with 75 equals 3R. So R, or radius, is going to be 25 centimeters. So we now have our radius. And to figure out our theta, we can just use our S equals R theta up here. So S is equal to 6 again. We still have the 6. Our R is equal to 25. And our theta is still unknown. We can divide both sides by 25. And we get theta equals 6 over 25. Or, if you put that into a calculator, you'll get 0.24. And because we use the radian formulas, we will say that our theta is in radians. So 6/25, or 0.24 radians. So the rest of the notes that we have, this is what we're going to be doing in class together. We're only going to do this part as the video, and the other part we're going to talk about in class, in groups, tomorrow when you get here. So hope that this makes sense. Bring questions that you have to class.